So I'm going to do something a little bit different in this video. I'm not going to do any mathematics really, or any physical interpretation. I'm going to talk about sort of the philosophy of this problem, and this is my opinion, so take it with a grain of salt. But in the series that I just did on this subject, we pretty extensively went through the derivation of the blackbody problem. We showed why the classical result why this result here was wrong, okay? So we showed why that was wrong, and we showed how this equation generated in the quantum case, or the discretized case, we showed how this equation is correct. It's correct from a theoretical standpoint, in the sense that this energy, when integrated over all frequencies, is of course finite. So this is finite energy under the curve. That's an important result. But also this curve matches experimentally with the radiation we observe from black bodies. So what I would like to discuss a little bit is this quantity here. Okay, so this quantity, and I'm going to copy this line out again because I think this is super important. Okay, so let's copy. Here we go, finally. Okay, so like I said, we took this factor, we multiplied it by our new average energy. And remember, originally we were calculating the average energy per mode. Well, this is not really true anymore. Strictly speaking, this is not the average energy per mode. This is really, so this I would say is an incorrect statement. And what we really did was calculate the average energy per photon, when we are at thermodynamic equilibrium. So it really causes us to ponder on this quantity. What was this quantity in the classical case? Well, in the classical case, this was what I called a multiplicity of modes, and it's also modes per volume per wavelength. Okay, so we went through, actually in this case, sorry, it's per frequency, because we converted it to per frequency quantity. So this is a multiplicity of modes per volume per frequency. And I may have screwed something up here a little bit, because really it's power. We get a power output. So it's also per time, maybe? I guess from a unit analysis, per unit time. So there's obviously a lot packed in here. But I don't think that, once again, I don't think that we can say this is a multiplicity of modes. I mean, remember what the original problem was. You have this this black box in space with this electric field, you know, maybe with some particles flying around inside. It's at thermodynamic equilibrium. It's in the vacuum of space. There's standing waves set up inside such that at the edges, at all the edges, that field is zero, right? E0. Any edge you take on this cube. Okay, that was our original setup, and we calculated this multiplicity of modes over here. I don't think that quantity is in the quantum case is really reflective of what's inside the box. And to say that I'm speculating is not really fair. I mean, we did the mathematics. Why is it, I think it's fair to ask the question, why is it that this quantity is exactly the same in the quantum case? So what is this quantity in the quantum case? And what it must be the multiplicity of photons. Now that's a weird statement to make. Another way to say it is that we're looking at the configuration of all photons. And when you take this all configurations of photons and multiply it by the average energy, of course you get the statistical average of the system. We've seen this many times in talking about statistical mechanics, thermodynamics, even in this problem in previous videos. This is how we derive this average energy quantity. But We essentially did a derivation that was purely about, okay, so what is this thing over here? This thing involved, remember, it involves standing waves, right? N equals 1, N equals 2. How does this mathematics that we did apply to photons? And once again, it's speculative on my part because, in my opinion, because I haven't done the mathematics. Maybe I could pose the question, and this is jumping into the quantum world, which I don't understand as thoroughly as I would like. But what if you solved the wave equation for all of the photons in the box? Do you end up with something like this? Do you end up with mathematics that reflects this standing wave equation? And remember, these were E fields. These were E fields. Maybe in the quantum case, we are looking at the wave function or something like that. Like I said, I don't know. I don't know the answer to this question. But I think from a philosophical standpoint, it's certainly interesting to look at this line of reasoning. Like, look at this connection here. In the past several videos, we literally went through every single step of this derivation. And I don't think that you can say that this multiplicity of modes of standing waves is the correct interpretation. Remember, this is an interpretation. This is an interpretation. The mathematics that we did was purely based on this over here. This, say the mathematics, the math we did is based on this model. Okay, but clearly we've converted our energy function. Our energy function is now E equals NH nu. This is a number of wave packets or photons. So how is it that this mathematics that we did still provides the correct result? And I think what we need to do, my gut, my instinct tells me that this model for a black body is less so about standing waves, standing electromagnetic waves that have zero field at the edges, and maybe looking at this system as a quantum system with all of these gaseous particles that are at thermodynamic equilibrium, looking at them in the quantum sense, in the multiplicity of configurations of these of this system, the multiplicity, it still works out to be this. So I would love to dive into this, but like I said, quantum physics is not, it's not a subject that I consider myself an expert on by any means, or even claim to understand it. But if you have any thoughts on this, I would certainly love to hear it in the comment section. If I've said anything incorrect or something that you disagree with factually, I would love to hear that as well. So please like and subscribe if you like this kind of stuff, and I'll catch you next time.